Imagine a material so strange, so otherworldly, that it breaks the rules we thought light had to follow. This isn't science fiction. It's the reality of a class of substances we call hyperbolic metamaterials. The name might sound complex, a mouthful of scientific jargon, but the idea behind it is a beautiful blend of simplicity and profound consequence. We live in a universe governed by physical laws, rules that dictate everything from the spin of a galaxy to the shimmer of a soap bubble. For centuries, we thought we understood how light travels through materials. It can reflect, like off a mirror. It can refract, bending as it enters water. Or it can be absorbed, warming the surface it strikes. But what if a material could do something entirely new? Hyperbolic metamaterials, or HMMs, are engineered substances. They don't exist ready-made in some cosmic mine. We build them atom by atom, layer by layer, with a specific purpose in mind. Their goal is to take our understanding of light and turn it on its head. These materials possess properties that are not found in nature's standard toolkit of elements and compounds. They are meta, a prefix meaning beyond, because their abilities transcend those of their individual components. Think of them as a symphony orchestra. A single violin or a lone cello can make a beautiful sound. But when you combine them in just the right way, you create something far grander, a symphony that no single instrument could ever produce on its own. So, what is the grand symphony these materials play? It's a symphony of light itself. HMMs can control the flow of electromagnetic waves with a precision we've only dreamed of. They can guide light around objects, making them appear invisible. They can focus light into points smaller than its own wavelength, shattering a long-held physical limit. This opens a door to a universe of possibilities, a new chapter in our species' long and intimate relationship with light. From the first fire that warmed our ancestors to the lasers that carry our global communications, we have always sought to master light. Hyperbolic metamaterials represent the next great leap in that ancient quest. Our journey into this strange new world begins with a simple question. What happens when you combine two very different types of materials, a metal and an insulator, in an incredibly structured way? You get something that isn't quite one or the other, but possesses the most extraordinary qualities of both. It's a testament to human ingenuity, our ability to look at the building blocks of the cosmos, the metals, the ceramics, the plastics, and see not just what they are, but what they could become. We are pattern makers, tool builders, and with hyperbolic metamaterials, we are learning to build with light itself, sculpting its path and unlocking its deepest secrets. To understand the magic of hyperbolic metamaterials, we need to think about how different materials treat light. Consider a piece of glass. It's an insulator, or what scientists call a dielectric. Light can pass right through it, bending a little as it enters and exits, but otherwise traveling freely. Now, think of a piece of metal, like silver. It's a conductor. Light doesn't pass through metal. Instead, the light's energy excites the free-floating electrons within the metal, and the light gets reflected back. You see your own face in a silver mirror because of this property. Dielectrics let light in, metals keep it out. These seem like two opposite behaviors, two distinct personalities for matter. Hyperbolic metamaterials do something truly bizarre. They exhibit both personalities at the same time. Imagine a material that, if you shine a light on it from the top, acts like transparent glass. The light passes through. But if you turn that same material on its side and shine a light on it, it suddenly acts like a reflective metal. The light bounces off. This is the core secret of an HMM. It has a split personality. It's a metal in one direction and an insulator in another. This isn't a trick. It's a fundamental property that emerges from its carefully designed internal structure, a structure we build with purpose. This dual nature is what gives these materials their hyperbolic name. The name comes from a mathematical equation, a dispersion relation, that describes how light waves can travel inside the material. For ordinary materials like glass or water, this equation describes a closed shape, like a circle or an ellipse. This means there are limits to the kinds of light waves that can exist inside them. But for HMMs, the equation describes an open shape called a hyperbola, an open, unbounded curve. This mathematical quirk has a staggering physical meaning. There is, in theory, no limit to the size of the light waves that can be squeezed into the material. This is a game changer. For over a century, a rule called the diffraction limit has dictated what we can see with a microscope. The rule states that you can't see details smaller than about half the wavelength of the light you're using. It's a fundamental barrier, a cosmic speed limit for imaging. But hyperbolic metamaterials, with their open, unbounded hyperbolic nature, can support waves with incredibly short wavelengths, far smaller than the light that created them. This allows them to capture and transmit fine details that would otherwise be lost forever. Evanescent waves that fade away in normal space but thrive inside an HMM. It's like having a special net that can catch the ghosts of light. How does this strange, direction-dependent behavior come about? It's all in the architecture. The structure of a hyperbolic metamaterial is what gives it its power. It's not about the chemistry of a new molecule, but the geometry of how we arrange existing ones. Think of it like building with Lego bricks. You can have red bricks and blue bricks. Separately, they are just simple blocks. But when you stack them in a repeating pattern, red, blue, you create a new visual texture, a new structure with properties that neither the red nor the blue bricks had on their own. The collective is more than the sum of its parts. This is precisely how we build HMMs. We take materials we know well, like a metal and a dielectric, and we arrange them in a repeating sub-wavelength pattern. This means the individual components are smaller than the wavelength of light we want to control. When light looks at this structure, it doesn't see the individual layers of metal and glass. It's like looking at a finely woven tapestry from across a room. You don't see the individual threads. You see a single, unified image. The light sees the structure as a new, continuous, and very strange material, a metamaterial. This structure forces light to travel in ways it never could in a uniform substance. In a normal material, light spreads out in all directions, like the ripples from a stone dropped in a pond. But inside an HMM, the light's path is severely restricted. The material acts like a set of invisible channels or funnels. It can take light that is spreading out and force it to travel in a straight, narrow beam, a phenomenon known as canalization. It can guide light along a specific path, bending it around corners in ways that would be impossible with traditional optics. We are literally building a roadway system for light. This ability to guide and direct light with such precision is what makes HMMs so powerful. We can design the structure, the thickness of the layers, the choice of metal, the type of dielectric, to control light of a specific color or wavelength. We can create materials that are hyperbolic for red light but ordinary for blue light. This level of control is unprecedented. We are no longer just passive observers of how light behaves. We are becoming the architects of its journey, designing the very fabric of the medium through which it travels, and in doing so, we are rewriting the rules of optics. So how do we actually build these things? How do we construct a material with features smaller than a wavelength of light? The process requires incredible precision, working at the scale of nanometers, billionths of a meter. There are two main recipes for creating hyperbolic metamaterials. The first, and most common, is the one we've touched upon, the layer cake approach. Scientists use sophisticated techniques like atomic layer deposition or molecular beam epitaxy. These sound complicated, but you can think of them as ultra-precise spray painting, allowing us to lay down one perfect atom-thin layer of material at a time. We start with a base, a substrate. Then we deposit a whisper-thin layer of a metal, perhaps silver or gold. This layer might be only 10 or 20 nanometers thick. For comparison, a human hair is about 80,000 nanometers wide. On top of that metal, we deposit an equally thin layer of a dielectric like aluminum oxide or titanium dioxide. And then we repeat the process. Metal, dielectric, over and over again. By carefully controlling the thickness of each layer, we create the alternating structure that gives the final material its split personality, its hyperbolic properties. It's a painstaking process of nanoscale construction, building a skyscraper for light, one atomic floor at a time. The second recipe takes a different approach. Instead of a stack of flat layers, this method uses tiny metal wires. Imagine a block of clear dielectric material, like a brick of glass. Now, imagine embedding within that glass millions of perfectly aligned, incredibly thin metal wires, all pointing in the same direction. These are nanowires, and they run parallel to each other from one end of the block to the other. When light tries to travel along the direction of the wires, its electric field can move the electrons in the metal, so it acts like a metal. It reflects the light. But if light tries to travel perpendicular to the wires, its electric field can't effectively move electrons from one separate wire to the next. The light mostly interacts with the dielectric material between the wires. So, in this direction, the material acts like a transparent dielectric. The result is the same. a material that's a metal in one direction and an insulator in another. The choice between layers or wires depends on the specific application, the color of light you want to control, and the manufacturing technologies available. Both paths lead to the same extraordinary destination, a material that can command the flow of light. While we often think of metamaterials as a triumph of human engineering, a purely artificial creation, the universe has a funny way of beating us to the punch. Nature, through billions of years of evolution, has stumbled upon similar principles. There are naturally occurring materials that, by sheer chance of their atomic structure, exhibit properties that are strikingly similar to our designed metamaterials. They may not have been created with the intention of controlling light in this way, but their fundamental physics follows a similar path. They are nature's own metamaterials hidden in plain sight. The most famous example is graphite. Yes, the same humble material you find in the tip of a pencil. Graphite is made of carbon atoms arranged in flat sheets like endless pages in a book. These sheets are called graphene. Within each sheet, the carbon atoms are strongly bonded, and electrons can move around freely, almost like a two-dimensional metal. But the bonds between the sheets are very weak. It's much harder for electrons to jump from one sheet to another. Because of this layered atomic structure, graphite behaves differently depending on the direction of an incoming electromagnetic wave. This structure, strong conductivity within the layers and poor conductivity between them, is the very definition of the anisotropy required for hyperbolic behavior. For certain frequencies of light, particularly in the terahertz and infrared parts of the spectrum, graphite acts like a natural hyperbolic material. It's a stunning realization. The stuff we use for writing is, from a certain point of view, a piece of advanced optical technology. Nature, the ultimate tinkerer, figured out that stacking conductive layers with insulating gaps creates unusual electromagnetic properties long before we did. This doesn't mean we can just pick up a pencil and build a super lens. The hyperbolic properties of natural materials like graphite are often fixed and exist only for specific frequencies. The true power of our engineered metamaterials is their tunability. We can design them to work exactly how we want, for the specific colors of light we need for a given application. But studying these natural analogs is incredibly important. They provide us with inspiration. They show us that the universe is rich with possibilities, and they serve as a crucial testbed for our theories, confirming that the strange physics we predict in our labs also has a place in the natural cosmos. The world of engineered materials is a vibrant landscape of ideas. In one corner, we have our hyperbolic metamaterials, built from sub-wavelength patterns of metal and dielectric to create a new uniform medium. In another corner, there's a different but equally fascinating concept, the photonic crystal. A photonic crystal isn't trying to pretend it's a uniform material. Instead, its whole purpose is to have a repeating structure with a size that is comparable to the wavelength of light. Think of it not as a new fabric, but as a sieve for light. This periodic structure creates something called a photonic band gap. This is a range of frequencies or colors of light that are forbidden from traveling through the crystal. If you shine light of that specific color on the crystal, it can't enter. It gets perfectly reflected. It's like a bouncer at a club who only turns away people wearing a certain color shirt. This property is incredibly useful for creating things like ultra-reflective mirrors or tiny light-guiding channels called waveguides. Photonic crystals are masters of creating forbidden zones for light. Now, what happens when you bring these two powerful ideas together? What if you take a hyperbolic metamaterial and then impose a periodic pattern on it, like etching a grid of holes into its surface? You get something new and even more powerful, a photonic hypercrystal. This hybrid material combines the best of both worlds. It has the unbounded all-angle light propagation of a hyperbolic metamaterial, but it also has the frequency filtering power of a photonic crystal. It's like having a highway system for light that also has traffic signals that can be turned on and off for specific types of vehicles. This combination unlocks a whole new level of control. A standard HMM can support a wide range of light waves, but it can be hard to excite them or select just the ones you want. By adding the photonic crystal structure, you can create allowed and forbidden states within the hyperbolic regime. You can sculpt the very density of states available to light. This allows scientists to precisely funnel light energy into specific modes, enhancing light-matter interactions in ways that neither material could achieve on its own. It's a powerful synergy, a collaboration between two of the most exciting ideas in modern optics. So, this is all fascinating science, but what does it mean for us, for our technology, for our future? The applications of hyperbolic metamaterials are not just theoretical curiosities. They promise to solve real-world problems and open up entirely new technological frontiers. One of the most exciting applications is in super-resolution imaging. As we discussed, the diffraction limit has long been a barrier, preventing us from seeing the finest details of the microscopic world, like the intricate workings of a living cell or the structure of a single virus. Hyperbolic metamaterials can act as a hyperlens, capturing those fleeting, high-resolution details and magnifying them into an image we can see. Another powerful application lies in controlling thermal energy. Heat is just another form of electromagnetic radiation, but at infrared frequencies. By designing HMMs that are hyperbolic for thermal radiation, we can control the flow of heat with unprecedented precision. Imagine a computer chip that, instead of using a bulky fan, has a thin metamaterial film that efficiently channels waste heat away from its sensitive components. Or think of a building coated in a material that radiates heat out into the cold of space at night, providing passive cooling without using any electricity. This is thermal management at a whole new level. The applications extend to making better sensors too. Many sensors work by detecting tiny changes on a surface. For instance, when a specific biological molecule binds to it. The interaction is often very weak. By placing the sensor on top of a hyperbolic metamaterial, we can dramatically amplify the light's interaction with whatever we're trying to detect. The HMM concentrates the light field right at the sensing surface, making the sensor far more sensitive. This could lead to medical diagnostic tools that can detect diseases from a single drop of blood or environmental sensors that can pick up trace amounts of a pollutant in the air. We are at the dawn of a new age in materials science. Hyperbolic metamaterials are more than just a clever trick of physics. They represent a fundamental shift in how we think about and interact with light and energy. From seeing the unseeable to controlling the flow of heat and creating a new generation of sensors, their potential is vast. Like the discovery of the semiconductor that led to our digital world, the mastery of these new materials could reshape our technology in ways we are only just beginning to imagine. The cosmos is full of rules, but it has also given us the intelligence to learn those rules and sometimes to build things that bend them.